So thank you again, Sudeep, for inviting me and for the introduction. And so welcome to all of you. Um, so I think you have the structure for the 5 days, and all the lecture notes are available in hard form, the bound book, as well as I think you have gotten USB as well. All the soft copies of the lectures are available. And I just spotted one or two editorial things, minor corrections, but I'll mention those as we progress to the slides so that we can correct it. Not many. I've just spotted one for today. Maybe there'll be one or two again for the next few days. These are mainly editorial typos and things like those. So the plan is that we have the first hour and a half today. And I don't know what form would you like. What I will present is more non-technical and relatively light. So I suggest that we can proceed straight away without taking a break. But from the next lecture onwards, and tomorrow probably, if we have a lecture for 2 hours, maybe what we can do is we can have a lecture for 50 minutes and take a short break of 10 minutes, and then again progress with another hour or so. And if we have an hour and a half, in that case, maybe we'll take a short break again for maybe 5 minutes somewhere in the middle. Whenever we think it's appropriate. Like if you're tired or I'm tired, just take a break. And if you don't understand anything, just interrupt. So let's make it more interactive. That's it. So feel free to ask questions. Feel free to interrupt and clarify things if you don't understand. It's also a challenge to incorporate all the different aspects of wind energy and wind turbines, because it's a very multidisciplinary area, both in terms of the content, but also in terms of the research that's going on. Very topical as well, because a lot of things are evolving, and even classical things of designing generators are also changing as well, because now, of course, the focus of this particular course is on structural dynamics and aerodynamics and control, mostly vibration control, but we'll also talk about power control as well, because they're kind of connected together for wind turbine. They're things which cannot be separated out, because there's an impact of vibration control on the power control and vice versa. So we can't kind of separate the two out. So we'll have to discuss about the whole thing in integrity. But one thing we won't go that much in detail is electrical generator part of it, which is by itself a big area, and also the connection to the grid. So I'll mention in the passing a few things, including the connection between the grid and the mechanical vibrations and grid faults and so on. But power system is a completely different area. So those with background electrical engineering would know that power system dynamics itself is also a subject that's actually considered by its own right, and a lot of research goes on in that area. So I don't think we'll be able to cover the power system dynamics here. So that's one thing we won't be able to cover. And that is connected to the grid connection, which is part of what's called the power electronics, actually, which also plays a very important role. So actually what I'm saying is that what I'm not going to cover before I start on what I'm going to cover. So power electronics part is again a topic by its own right, and a big area as well, not just for wind, but for renewables in general, microgrid and other power generation connections. And that's something also we won't cover, because again, that's a completely separate topic. And finally, electrical machines and generator again is again a very classical area, but again a topic in its own right. As we are not going to cover things like the systems economics, because that's also a very important thing, how the market behaves. Because all the things we're going to discuss will eventually impact in the generation of power. So we're dealing with something which is actually a commodity here, where we are selling power, right? So unlike a lot of other engineering things that we deal with, where we don't actually consider the pricing as such. I mean, we do optimize things. We want to minimize use of materials. We look at ergonomics. We look at minimizing the cost, minimizing the time. A lot of things are looked at, but we don't really look at the integrated cell of the product that's been designed by the engineers. But unlike that, here we are actually dealing with a system where not only we just produce the power, but we also actually have to sell it. So we're dealing with what is called the TSOs and DSOs actually. So transmission and the generation and the distribution system operators. So the power companies who are selling the power are also connected, and that actually decides how much power should we generate. And if you have to decide how much power we are generating, that means we have to apply some kind of control to control the generation of power. And also there's stipulations on why we have to be connected to the grid and to what extent. So these are also very interesting things I'm saying, but these are things we are not going to cover in depth because again, these will be separate things by its own right. But bear in mind, all the things which I'm going to discuss here will have direct or indirect impact on those things as well. So the point is that unless you know the basics and fundamentals here, we won't be able to do justice to those things. So bearing that in mind, let me just begin with a brief introduction of wind energy and wind turbines. So why do we need to look at wind energy? And, well, one thing which I have written down here, and since yesterday I've been here, and I found out that there's also power disruption going on quite frequently, as it happened just now. You can see. I don't know whether it's a problem with the grid or it's a local problem here, but anyway, you might have faced this in the last 24 hours a few times. And this is primarily because sometimes the grid cannot cope up with the demand and the supply. So electricity is also being consumed, meaning that you have a demand for electricity, and that has to be supplied. If there's any mismatch between the demand and supply, then either you have to control the demand and supply, or there's another option available. I think somebody of you here mentioned that the PhD research is on battery. So that's the third option available to you, which is storage. But storage is expensive, meaning that if we generate power and if you have to store it, then we have to get a battery, and the battery costs. So meaning that you have to add that to the cost of the power as well if you're selling the power. So, but that's one way to manage between the mismatch between the demand and supply. So obviously, the reason why we need generations like wind is, first of all, it's clean because we get it from wind. We don't burn fossil fuel, so obviously we are not generating any exhaust out of it. So therefore, we're not producing carbon, either directly or indirectly. And therefore, obviously, it's clean. And obviously, it's also renewable because if you have other sources like, for example, might say gas or shell gas, which you can actually burn completely, complete combustion, still not produce carbon perhaps, but it's not renewable, meaning that once you exhaust part of it, it's gone. So after a few years, obviously the resource will be depleted, won't have any of those left for use. Like that, wind is obviously renewable because every time you use wind, again you get more wind because wind is always circulating. So it's more perennial. And obviously, because of these two reasons, wind energy is very attractive. There's also a third point. And that is, in a situation, just I mentioned about the problem with the grid. Places where you cannot have grid because of either problem with the terrain or the cost involved in but the cost involved in installation and deployment of the grid might be significant. And the question is that who then will pay for the installation of the grid? Because there'll be some amount of resources needed. And if you set out a grid, if you can even, not always possible, then the question is that who is going to pay for it? If you charge it to the state, then it's taxpayers, and that has to be recovered in some form. If it's a private company, then they'll actually make a profit out of it. So there's also a cost again, consumers. And if it is actually either the generation companies or the transmission companies, they'll then add it to the cost of the electricity, which is going to be passed on to the clients of the consumers there. So eventually, there is also a cost implication. So in these cases, and also there's an issue with a huge investment, initial investment cost, even if that can be possible to be invested. So in such situations, instead of having a power grid, you can try to have sources which are renewable like wind, and that's because they're local. So that's one important thing. And this is technically, in the terms of energy, is called energy security. So that means I'm not taking energy from anywhere else. And that means I'm taking the energy what's available here, right here, and therefore it's more secure. So if I use resources I have, like solar, like wind, if you're near the coastal region, you can also use wave and tidal, and have this in the mix along with maybe some thermal power plant or gas-fired, some hydro storage. Then you might be able to actually supply power in a more reliable way without actually having the grid and without having any impact of fluctuation of demand and supply on the grid. So that's actually a third reason as well, and quite important because it's possible for wind, obviously, for other sources. Now, there are two aspects to it. Like one is onshore and offshore. And onshore wind turbines have been criticized mainly because of visual impacts they have, impacts on other ecological systems around it, impacts it may have on tourism, for example. It's a nice place and you don't want to impregnate the place with a lot of wind turbines. Tourists would not like that. Like, say, for example, you can put wind turbines on top of the mountains to get more wind. But if you do that, like if the mountain is used for a skiing resort, then that's going to be protested for, because obviously that will impact on other activities and so on. But also it might impact on, say, the birds which might be flying. So that's why, even though places onshore might be attractive, but it's not actually physically possible, won't get a permission or planning permission to put the wind turbines. The other problem also is that if you're onshore, then because of the terrain and surface roughness and other things, you'll be generating a lot of turbulence in the wind. And turbulence is something which is not desirable, because you really want wind, but we want wind which is flowing without any turbulence, with a stream steady flow. But if you have turbulence, what happens is, first of all, it will actually have an impact on the fluctuation of the speed. That will have to be filtered somehow, whether it's done at mechanical level by using some kind of controller, a mechanical controller to change the angle of the blade, and thereby changing the aerodynamic characteristics, or will have to be done in some sense by the electrical side by using power electronics, so that all the AC components are converted to DC and so on, and then converted back to AC. But there is also another important detrimental effect of turbulence and vibrations, and we'll see that actually in the slide I'll show you in half an hour or so. It actually causes fatigue damage to components of wind turbine. And the first component which is affected is first the blade, because it's flexible, a very long flexible structure. And typically 5 megawatt wind turbine, which is quite standard now, will have a blade with a diameter of, roughly speaking, 126 meters. So it's a flexible blade of diameter 126 meters, sitting on the top of the tower, which is say 80 or 90 meters high. So you can think of this system, which is a very slender tower with very slender blades of that dimension, and the amount of hydraulic load it has, And on the top of that, you have a room, which is actually maybe slightly bigger than this room, and it's called the nacelle. What's in that? Inside that nacelle, you have the transmission, you have the gearbox, you have the electrical generator, you have the power electronics, you have the control systems. So everything is there in that room. And that's actually sitting on the top of that slender tower, which is probably 5 or 6 meter diameter at the bottom, goes up to a diameter of maybe 3 meter at the top, and that actually is sitting there. And roughly speaking, that's 70 tons. You know? So think about that, like you have a few cars sitting on the top of that tower, and the blade, which is actually hit by the wind at a speed of 30, 40 meters per second. I mean, there are a few hundreds of cars moving at a speed of 100 miles per hour. And obviously, the damage it can cause to various components. The blade, it can cause damage to the bearing plates, it can cause damage to the actuation system, it can cause damage to the gearbox. And gearbox, I mean, if you look at gearbox which are in operation in wind turbines for over a year, you will find that how damaging they are. So essentially, this turbulence will have a detrimental effect to the overall condition of the mechanical systems. So therefore, if you can get rid of turbulence, it's ideal. So that's one of the reasons why people thought, well, offshore is better because we don't have much turbulence there. Because we don't have the terrain, therefore the wind is actually more uniform without any turbulence. It's not always correct. We'll see that also in one of the slides. And something we see that there is actually an amplification of turbulence when you're in offshore. Not always, but there are cases. Generally speaking, you expect less turbulence and less load, less fatigue damage. And obviously, you have higher potential of offshore wind power because you can go high up, you can get more wind speed unobstructed, generate more power. So the power density obviously increases if you're going offshore. Now, obviously, we'll look into the introduction to modern wind turbines and what kind of components it has. Our focus obviously is going to be on the structural dynamics, aerodynamics, controls. I mean, there are also hydrodynamics, geotechnics, generator power electronics. We won't go that much in detail. I'll give you some element of hydrodynamics as well, because obviously we are talking about turbines. We need to understand it. Geotechnics is a very different area, so we won't go into that again. And then I've already mentioned to you about the communications, power grid, and electrical markets. They are also integral part of the overall systems. But again, that's not going to be the focus of the rest of the lecture. And that's why we have always spent some time in explaining what the impact of those might be to you. But if you have any specific questions in relation to any of these, feel free to ask me. And finally, I'll give you some exposure to the more topical areas, which is basically the floating offshore wind turbines. And floating offshore wind turbines are getting popular because of, as I said, problems with onshore wind turbines, but also we are filling out with land. So we don't want, or we don't have space actually available. So it's better to go offshore, and we can have a lot of wind turbines in offshore region if we want. So obviously that's a big area of development. And I'll tell you about various systems which are normally used and so on. Well, obviously taking a bit more time in discussing about these things here, but the later part of the slides will be faster because a lot will be pictorial representation of things and so on. So let me move on to the next slide. And I've already emphasized the impact that interdisciplinary subjects might have together in the case of wind turbine and analysis of wind turbines. And it is sometimes quite astounding to see how electrical grid fault might have an impact on the vibration of the tower or the blades, and how the oscillations, the low frequency oscillations, are transmitted to the generator side. We've already emphasized the finiteness of the fossil fuel, potential of wind, because it's pretty much exists everywhere. Oil is a resource which is available only at limited places. You might be near the shore or maybe offshore, or not so close to the shore, meaning that you can't harness the ocean energy. But irrespective of where you are, we always have wind. So obviously, wind turbine is available to everybody, and therefore it exists everywhere in the world and can be used. The other thing is that because the technology is available in aerospace and for offshore, say, oil industries, and people have already worked on like machines and dynamics and aerodynamics and geotechnics, we can bring in already existing expertise from various areas and put those together with certain adoption to use for wind turbines. So we can actually do that. So obviously, we don't need to start right from the beginning. We know something about all these things. So we'll use those and see how we can actually design a wind turbine or do better to generate energy from wind turbines. Of course, there are two different important things here. One is a vision. That means you need to actually have a vision to use the energy in a different way. And that's where the political will comes in. So the policy. So political will means policy. So the government or whoever is actually managing the system will have to emphasize on what policy should be taken to generate the energy. For example, if you give incentive to fossil fuel, obviously, and because of cost, they will always be preferred. But if you do not give that incentive and allow fair competition between various types of energy generation, then that will actually make a difference. So all these things, these policy decisions are very important, and they will actually also be important because they will also ensure that supports the research, because the way wind energy has developed, typically from the 70s, where there were consumer groups in Denmark, they started this energy generation from wind, but slowly they started grouping together. But a lot of support from the state came as research, but also industry invested a lot in the 80s and 90s, and testing, the regulatory reforms, policy, as I said again, and interconnection with the networks and so on are also very important. So all this will have to be somehow incentivized because of the added benefit we get from the renewable energy. So these are necessary things. And because of favorable conditions, the reemergence of wind actually happened in various places. Just to mention briefly about the global warming and climate change. There's a lot of debate whether it's anthropogenic or it's natural, but definitely there is a risk, and highest risk of human being on Earth at the moment, in the sense that the forecasts roughly say that soon enough there'll be 2 billion of people on the planet lacking clean water. Food crisis, which is actually going to be also another area which we haven't looked at or haven't focused to that extent, will be also an important thing. They're also connected to energy because they are all effectively either because of use of energy necessary for all these things to happen, or somehow connected. And therefore, it's very important to also consider the energy and impact on water and food as well. Also, the reports from IPCC, though have been debated from various groups, but it's more or less, I mean, the cause may be debated, but the fact has not been disputed anyway, and that is the effect of mean sea level rising 5.9 meter in the year 2100, and then that figure was revised actually within 6 years, and because previously it was 0.6 and it was revised to 0.9, so people are re-estimating things, and things might actually become worse faster than we think. So if you think that the effect of whether you call it an anthropogenic climate change or a natural cycle change of climate, it is changing fast, and actually it's accelerating. That's what is very disturbing and concerning. And similarly, the temperature rise is also another thing, and that we have actually evidence of loss of ice sheets and melting of ice and so on one side, but then again, forming of ice on the Antarctic. So there is a disruption going on, and all these are real facts. So obviously, the cause has been disputed, but the effect is actually more or less acknowledged by all the groups. There's another interesting slide, and if you can see, slide on the left gives us a graph. The blue one is the world population, and pretty much in line, the energy and the electricity demand is increasing, as you can see, quite in an exponential fashion. And then we always have thought that, well, what might happen is that the fossil fuel and the oil might be actually discovered, and reserves might be available. We'll be able to come back to the requirement very soon, what we have found. But that's true because until about 70s, there's a peak in terms of volume of oil discovered worldwide. This doesn't include the shale gas, but even if you add that, it's not going to be a huge amount overall, and it's also not available to everybody. They're localized the only ones which are lower are this advanced combined cycle or the conventional combined cycle. These are actually using electricity at the lower levelized cost of energy. So if you take the levelized cost of energy, then wind is performing if you're comparable to the conventional coal. Now, so onshore is quite attractive. If that's the case, then should we not go for more onshore, trying to find places where you can put wind turbines rather than trying to go offshore? And of course, I've told you about the advantages of going offshore, but is it worth doing that? Now, obviously, one of the things is that if you take the onshore wind turbines, one technical challenge we're facing is that the size of the wind turbine. So I've told you about other problems it might have, but also the onshore wind turbines might be reaching their limits in terms of what they can actually grow to a size. And that's because if you want to put a wind turbine, which is, say, having a tower height of 100 meters with blade diameter, say, even bigger, like 160 meters, then you need some kind of spacings. So that means the land that you need to put a sizable amount of generation capacity, say if you take 10 megawatt wind turbines, and if you want to have a capacity of, say, 600 megawatt, you need to put 60 of those. And 60 of those, if you have to put in a grid, say a 15 by 4 or something like that, you can calculate the amount of land that we need. So obviously, that will put a constraint on the size of the limit of the wind turbine. And also designing all those things will be challenging. So onshore, we are now reaching the limit. For offshore, there's no limit because obviously spacing, we have fairly large space available offshore. We don't have any conflict with the places where people are living, and obviously we can arbitrarily grow in that sense. Obviously, the visual constraints are there, but also there's another important thing, which is noise. And one of the main objection of onshore wind turbine is basically the generation of the noise. That's actually a problem mainly for urban wind turbines. So if you're actually putting a wind turbine in the city, then what happens is that the wind turbines are smaller in size, and that means to generate a power, the blades need to rotate at a higher speed. There are two impacts of that. One is, first of all, that generate a lot of noise. Second thing is that if you have higher speed, there's more wear and tear. So obviously you're damaging your gearbox, your braking system, and electrical machines sometimes. And effectively, it will not work for very long. In fact, after a few years, it will break down. That's the experience with most urban small-scale wind turbines. Now, having said that, I think there's a potential for doing research and looking at those wind turbines, which has not been done, and simply because the big companies are interested in bigger wind turbines to generate more power. And they have invested a lot in looking at the condition monitoring, looking at the control systems, and so on, for big wind turbines. But for small wind turbines, there's no major player. Therefore, no one has looked at optimizing a small wind turbine. What impact it has, what's the cut-in speed, what should be the ideal control, how to actually decrease the noise, how to look at the condition monitoring. So for small wind turbines, nothing really has been done. But that's because there's not been interest or not much of interest in the R&D in small wind turbines, because like a big company like Siemens would be interested in big wind turbines, or Vestas or GE, but they don't actually design small wind turbines. So therefore, they haven't invested in R&D. So obviously, noise impact is another thing. And for offshore wind turbine, you have none of this. So there's no visual impact, there's less turbulence, there's less noise, and obviously, offshore wind turbines can produce higher power compared to the onshore wind turbines, same height and steady wind flow. So floating offshore wind turbines, possibly large size, like I've said, 5 to 10 megawatt, but I think people are now designing 20 megawatt wind turbine, and that will actually minimize the cost of integration. Challenge in case of floating offshore wind turbine will be finding the relevant technology for the support structure for floating wind turbines. Now, obviously, we can take things from the oil industry to work, but there is a problem, and that is the wind turbine as such is a very different type of system than an oil rig or oil extracting platform. First of all, they're very flexible, as we've seen, whereas most oil rigs are very stiff, short structures. Second thing is that you have lots of machineries in a wind turbine, like generator, power electronics, all these gearboxes, rotating machineries. And oil rigs, you don't have that many rotating machineries, and that's another big challenge. I mean, if you're dealing with rotating machineries, we know from our experience in cars and existing machine shops and tools that it's a big challenge. Then you're now talking about huge rotating machineries, which are actually sitting at the top of this 80-meter tall tower, this huge wind coming in, with no access you have now. So how would you actually monitor the condition of those things? So that's a big challenge, actually. So we have to use relevant technology, but we have to also adapt it in a way so that we can actually change it for the wind turbine and wind energy. Construction feasibility is there. People are now constructing with large ships and barges. They take the different components of the wind turbine and then can be installed. And people are looking at various kind of installation techniques, plants and machineries, because if you're talking about, say, putting a steel tube on the top of the foundation, what sort of precision is needed in law? So obviously, all those things are very important. People are also looking into that. Various types of construction machineries and plants have been developed, and they're trying to use those for wind turbines. This is a map showing the potential of nearshore wind turbine, nearshore wind power turbines. And you can see that the blue actually is the lowest, and the red gives you the highest power available. So let's look at the places where the highest wind power. So this is Russia, parts of Siberia and so on, but the remote places actually. And again, this is Canada. So you have very high wind power available, Canada and Russia. But there's a problem. If you have such a high wind speed or wind power, then designing something that can extract power sustainably and continuously is a big challenge. Really, the power that we actually generate is typically limited to wind speeds up to 15 to 20 meters per second. Whereas in this case, obviously, these are places where you have very large wind resources. So even building a wind turbine is a big thing. It's a big problem. So it's not much of use to us. We can forget about this red and the orange part because there's very high wind speed. Ideally speaking, this is where we have actually like dark yellow to light yellow. It's ideal because this is where we can build the structures which are sustainable. They can actually bear the load. Machines can operate properly, extract power. So if you look at the yellow and the dark yellow and the light yellow places, typically this is slightly darker, I would say. Parts of South America, which is good. Obviously, south of America and Mexico is good. So that's why you see a lot of wind turbines in Houston, that region as well. There's some in California, of course, there as well. And then obviously you have a lot of wind energy production in Europe. This is typically, you can see Denmark, and this is like those who have 1 and 2. So number 1 and 2 would correspond to these two colors. Australia again has a lot of wind resource, but again it's very high. And then if you look at India, obviously parts of Africa over here, but again India is ideal in that sense, and China as well to some extent. That's why currently, we leave out Europe, most of the growth in the wind energy sector is taking place in China and India. So Chinese government is also investing heavily on offshore wind turbines, and obviously in India also there's been a potential for wind turbine and wind energy, and there's also a thrust now to look at offshore wind energy. But also from the climatic point of view, the wind resource point of view, I mean, we are in an ideal situation to extract energy, similar to as we have in Europe. So it's an untapped potential for us. I mean, I don't know exactly the estimate and whether our site wind climate classification has been done, but I think there's been some work done by CIVET, Center for Wind Energy Technology. Yeah, but not a full report probably is available. Looking at what sort of resources are available and so on. I think there's some report I've seen by Ministry of New and Renewable Energy. They've done it for solar and some for wind as well, but I think it's still incomplete. So to assess the amount of wind available from offshore potential and onshore as well, but there's still a huge amount of untapped potential. So in conclusion, I think India has a good offshore wind power potential, the nearshore deep zone region. So nearshore is basically between the 20 to 30 meter water depth, going beyond up to 50 to 60 meters is deeper. And that's where most of the offshore wind turbines in India are placed. So that's the area where in India we have a lot of potential. So yeah, so conclusion, it's an appropriate technology for us to exploit and generate power from. So going slowly into a technical area now, and this is the impact of the growth in size of wind turbines. So historically, so this is it. It's a bit of history. So starting around 1985. Early years of wind turbine generation. There was one wind turbine was built sometimes in 1940s in the United States with a very high generation capacity. But since then, nothing happened. There was a thrust in renewable energy and wind energy around the time when the oil crisis happened, 1970s. And then the wind energy and wind turbine technology consistently took off from 70s and 80s onwards. And this is 1985. And the capacity of the wind turbine is, you can see, 0.5 megawatts. So 500 kilowatt machine was what was designed and built and operated. And then, obviously, as time progressed, technology also improved or progressed. By 1990s, typically 1991, 92, you can see that the wind turbine size has been increasing, but still we were less than a kilowatt range. It's 1995, 97. We're talking about 1.3, 1.6 capacity. In fact, though this is what conceptually was possible, but most of the wind turbines were less than 1 megawatt. In fact, when I started my research in wind energy back in 2000, 2001, I would say, the largest size wind turbines which were commercially available was 750 kilowatt. And there was a paper written by Thompson from Resort, Denmark, where they first observed some problem with vibration in blades. And this is a stall controlled wind turbine. I'll come to those later, but essentially stall control is that you basically change the angle of attack in such a way, or change the shape of the airfoil so that at some point the wind acts in such a way that the wind doesn't, the turbine doesn't rotate, it stalls. basically an aerodynamic phenomena where you stall the motion of the turbine based on aerodynamic design. So in those cases, when the wind turbine blade stalled, no power was generated, it was not rotating, but they saw severe, violent vibrations of the blade. And they thought it was due to some kind of a negative damping because of air elasticity. And so they analyzed it and they developed new materials with damping in the blade to suppress that. But to their astonishment, they found that that vibration was not suppressed. But soon enough, they actually realized that as the wind turbine size grew, the tower height increased as well. So what was now happening was the tower was a flexible body, and the blade was also another flexible body. And because of the nonlinear interaction between the two, there was actually a gyroscopic coupling, but also due to a nonlinear interaction between the two, there was a coupling, and that actually was the cause of the vibration. So it was not exactly aerodynamics, but because of the growth of the size of the turbine and the structural dynamics coupling happened. And they wrote a paper sometime in 1998 or 2000. That was the time when people started looking at even vibration dynamics of the system, because until then, the wind turbines were small enough. You can see that if you have a tower which is 20 or 30 meter high, you really don't need to worry about designing a tower for 20 meters. And the blades would be pretty much sitting on the tower as if it's a steep foundation. So this is when all this vibration problem started. Blades becoming more flexible, towers becoming flexible, and so on. And then their elasticity obviously also dominated. So you can see that 1995, 97, it's all in the range of 1 megawatt. And 1999, so around 2000, so this particular millennium of the century has seen the growth in the size of the wind turbine. So this is where typically first 2 megawatt turbine was designed and built. Vestas machine, then they also had a 2.3 Vestas machine, which was the most popular machine for a pretty long period. So between 2001 and 2 and 3, till about 2011-12, this 2.3 megawatt Vestas machine has been very popular. And if you look at all the wind turbines built around that period, that machine has been like used heavily. They sold that product extensively all around the world. But while that was commercially the best product available and used by people, the growth of wind turbine obviously progressed. And in 2003, 2001, 4.5 to 2003, 2005 is the year, again a landmark year, when the 5 megawatt wind turbine was built. And this is the one where I said it's the 156 meter rotor diameter. So the blades are 63 meter long. So the diameter is 126. So this is where all the problems that we see with all the dynamics and vibration and aerodynamics started. And in the last few years, people have designed 8 to 10 megawatt wind turbines, which are 60 meter long. And obviously, currently still growing, and a 20 megawatt concept design is now being produced. So in some of our research, we have used 5 megawatt, but also we've used a 10 megawatt wind turbine data. It's available in some of our papers. We haven't done work with the 20 megawatt, but that's being conceptually designed, as I said. And in fact, when this 1 megawatt size was reached, people said that the wind turbines can't go any further because that's really the limit that has been reached. But as you can see, it has actually grown even beyond, and that is primarily because of the fact that aerodynamic stresses are not increased even if the size of the wind turbine increases. And you can do a bit of geometric similitude on this. I don't think I have it in my notes, but I might actually do it to show that why is it. By using simple geometrical analysis or geometric similarity analysis, we have to say which stresses actually vary with which parameters and so on. And we've shown that the aerodynamic stress in the blade, the flap wise bending moment and shear stresses and so on, they don't actually increase with the increase of the size. And that's one of the things why we have actually been able to increase the size without increasing, without any significant improvement in the material aspect of the blades and so on. And of course, if you have a bigger machine, a bigger machinery, bigger wind turbine, obviously there'll be a lot of gravity loads, so there'll be higher gravity loads which will have to sustain. But the aerodynamic stresses are not changed. So we need to be critically looking at these wind turbines, and because of the size of the blades, flexibility, vibration issues have become more critical. We need to protect these large wind turbines against vibration and use structural damages as well. So that's why the structural dynamics part is so important. So I think it's about 50 minutes now. Do you want a break now, or should I just keep on to? I think the lecture is going to be started at 11:30, so we'll finish around 1 o'clock, say. Maybe 10 to 1, so that will give you some time for interaction and so on. So if I stop now for 5 to 10 minutes, then we can continue for another 50 minutes after this. Okay, let's take a break. It's heavy on the eyes, and I've been talking for a long time, so your concentration level goes down. And I need a bit of water to drink, so it's a good excuse. Is everybody back? So this is an area which has been, as I said, when I started working on this, it's roughly around 2002 or so. At that time, a lot of the things we are looking now didn't even exist in the form that we are doing. And in terms of interest and so on, I mean, obviously some companies were already interested, but not many companies were there. But just recently, I was talking to a colleague of mine in Aalborg, and we're counting, and like even in the offshore wind, the number of industries working have grown in exponentially in number. Hardly there are a few at that time. Now there are at least hundreds of companies there. So the growth has been very fast, actually. And obviously the requirement of personnel in these places are also very high. Research groups are also obviously very active now all over the world. And in terms of publications also, like typically I get at least on an average 4 to 5 papers to review every week, actually, and specifically focusing on wind turbines, but also on offshore wind turbines. So I think offshore wind turbine is actually an emerging area. So anyway, coming back to our talk, and we're now slowly, as you see, getting more on the technical side of things. So the reasons for growth in wind turbine size has been primarily, so you can see this is 5 megawatt, but this has gone beyond, obviously, is economy. So if you build something bigger, you have economy of scale. And like if you take the 10 megawatt, and in an array typically you can have, say, 40 to 60 of those, then 10 times 60 is 600 megawatt. So now you're able to compete with a standard conventional power plant, if you're, or you can produce to that scale. Obviously, you can maximize the power output and using various control strategies. And then the offshore development also has an impact in terms of the growth of the wind size. But obviously, this is phenomenal. And in fact, I know about this 160-meter blade, which I have a friend who is and a colleague also working in Enrel in Colorado. And when they were testing the blade, we were communicating. So now they say that they are probably going to test a 20 megawatt wind turbine blade. So if that's the case, now we're crossing the limit of 200 meter actually. And if that happens, then not only vibration, but also that it's also vibration, but we find that the critical flutter speed of the wind turbines also will be an issue. And we have done some work on that as well. And so the blades are now going to be like bridges, actually, almost. So the structural dynamics obviously brings us to the vibration problems. And longer blades are very flexible. Blades are now a limiting factor in the design of even larger wind turbines. That's really causing the main problem. What happens is that if a blade fails, then obviously there's a technical failure, and obviously there are repercussions for that. More importantly, the share price of the companies who are producing the blades actually goes down, and that is what they're actually afraid of. So the market price and the effect in the stock market. And so it has happened to Vestas once. It's happened to our company in India as well. We're originally a Danish company, now working with India, Suzlon. And Vestas also had similar problems where one of their offshore wind turbines actually toppled over. And the recovery cost of the wind turbines is massive because they had to send down divers to take the whole thing out from sea. So if the wind turbines fail, it's actually a huge cost in terms of recovery, in terms of environmental impact, in terms of the share price in the market, and so on. So the structural dynamics have to be taken into account, and the vibration becomes a very important parameter which threatens the stability of the entire system. So these are some examples of why you need to look at vibration. Obviously, it's very clear. This is one. This is the second one. The third one. You can see these blades have failed, but just to point out that this one is actually the nacelle. And I told you that nacelle is a room like this, even slightly bigger maybe. It houses all the different machineries in it. And finally, this one. So, obviously, wind turbines, or what they used to call windmills, have been historically been looked at by people, and typical capacity per se of the order of kilowatts. That has grown from kilowatts to megawatts now. So that is really the difference between what is called a windmill and a wind turbine. A lot of times, people who are not well aware of the development and growth in wind turbines, it's called the wind turbines a windmill, and they ask about windmills. Essentially, what their meaning is basically the old concept of wind turbines, which are primarily based on lattice towers and the turbine sitting on the top and generating the power. And the idea was the power generated would be used to do some kind of mechanical work rather than producing electricity. So maybe pumping some water or something like that, or grinding some wheat and mill and so on. That's why the name mill comes from. And the wind turbine is really where you use the power, the mechanical power is converted to electrical power, and then finally connected to the grid. Essentially, what we're dealing with is an aerodynamic force of lift, which is causing a torque on the rotating shaft, and this mechanical power is eventually converted to electricity. So the key things to understand, as we'll see, is really the lift and the drag, as for any other airfoil, like in aerospace industry as well. It's not possible to store wind, so whatever wind you have to generate and use immediately. That's one of the difficulties. I mean, you can store the electricity, but then you need a separate storage system, obviously. But there's no way you can actually store, like in a hydro, you can store in fossil fuel, you can store fossil fuel, you can't do that. So obviously, variability and fluctuation in the wind is a big concern there. Because if I have a certain demand and I use wind to generate and supply the power, but if wind is not there, obviously you can't do that. Or if there's more wind than I actually need, then there's going to be grid instability. Because if you feed more power than actually the power that you consume, that will actually cause a slight increase in frequency. Whereas if your demand is higher in the power system, and your load is actually basically higher, supply is less, then you have a drop in frequency. But say you're not allowed to actually go beyond 50 hertz plus minus 0.5 hertz. So the drop in the frequency is actually very important. That's why you need to actually match these two. Also, wind is not transported. You can't actually say, well, we have enough wind resource here in Silchar, let's actually get a pack of wind and then export it out. It's not possible. So you have to generate power, and you can't generate power and then export it. Substructures of wind turbines. We'll look at all these things now in more detail. So now I'm giving you an overview of what is going to happen in the next few days, very briefly. So this is actually the wind turbine, how it looks, and with all the subsystems of the wind turbine. So this is the foundation. Now, foundation actually costs a lot, roughly 20% maybe. And offshore is very high as well. So it's a critical component as well. The tower, and typically it's a steel tower, but now also designing concrete or composite towers as well. And that's actually a big area of research, because if you can reduce the cost of tower, you can reduce the cost of the turbine by 15, 20, 30%. So this is 20%, say this is roughly 15%. The blades actually are very important, very expensive as well. Like, to give you an idea, the 5 megawatt turbine, the blades are 17 ton each. So if you look at the blade, 3 of those will be roughly 50 ton. And the nacelle is roughly, say, 70 ton. Okay. And the tower also is maybe another 80, 90, 100 ton. So the amount of material used is significant. So the nacelle sits on the top of the tower, but there is a yaw bearing here, and I have a small wind turbine model of various components. I wanted to bring it to you so that I could have shown you all the different systems. One of the companies gave me a small model for teaching in the class to show you, but I couldn't bring it because it has a lot of sharp objects and things like those, so I was scared that it might be objected to. But roughly speaking, here is what you see is basically this nacelle is a room like this, and sitting on the top of this tower. The bottom diameter is roughly, say, 6 meter or 7 meter. The top is roughly, say, 3 to 4 meter. And the nacelle is sitting, obviously, there's a bed plate here, there's a yaw bearing, and this yaw is controlled by a yaw controller. And also there is a hydraulic damper which controls the damping motion for the yaw. The reason we need the yaw is because if the wind is blowing from a certain direction, you need to change the direction of the wind turbine to face the wind. And the yaw is basically done for that. And yawing mechanism, I mean, you can't completely turn it, but maybe plus minus 15 degrees is what you can do. Now, along with that, obviously, you also have an option of, so this is yaw is in the, if you look at this axis, the yaw is rotation along this axial direction. This nacelle can also move and pitch in a certain direction. So there's a pitching in that direction. So yaw in this direction, and this is rotating. So obviously, you can see there's going to be a gyroscopic coupling here. Because you have 3 axes of rotation. So this one, and this is a yawing. So obviously, there's a moment which is created by this, which will be counteracted by a gyroscopic moment, or the yawing will create a gyroscopic moment as well. So you have to do 2 things. When you write down your equations of motion, you need to count for that gyroscopic coupling. First of all, you can do that by using Lagrange Hamiltonian equations and effectively incorporate that there. And the second thing is, because of the gyroscopic coupling, you have some additional terms which actually creates some effective negative damping. So you have gyroscopic effect not just in the stiffness, but also in the damping terms as well. And this is actually the problem I was mentioning about this wind turbine in 1990-2000. This had this stall-induced vibration. That was because of the gyroscopic coupling of the damping between this system here. So that caused. That's why by introducing additional aerodynamic damping didn't help actually. Changing the material didn't help actually. Because it was really the fact that this was rotating, this was moving, that coupling caused the problem. And then you have a hub here, you see, and the blades are connected to the hub, and the connection here, you have some actuators. That actuator allows to turn the blade, and that is called the pitch control. So you have the yaw control for the nacelle, you have the pitch control for the blade, and that is done by an actuator which is connected to the hub here. And inside the nacelle you have, obviously, this is the slow speed rotor, because this is rotating at a very slow speed. Typically, for the 5 megawatt machine, the rotational speed is 0.2 hertz. That means once for every 5 seconds. It's very slow. And eventually you have to generate electricity. And what is the RPM required for that? Say if you have 50 hertz for generators, you have some electrical engineers here, right? 1500 RPM, right? So if you, depends on the poles. So if you do a bit of go back to your machines course in your second year maybe. So what happens then is you have a very slow rotation here, which is roughly speaking of that order, say 5 seconds is what it needs for one cycle, 0.2 hertz on the low speed side, low speed shaft. The high speed shaft, the generator side, you need 1500 RPM. So 1500 RPM is what is the hertz? So equivalent to yeah. So 28 by B. That's right. That formula. Yeah, exactly. So then now you can calculate the gear ratio needed, right? So therefore, you need a very heavy gear to transmit that power. So this is 0.2 hertz, and this is 50 hertz, right? So you need 1:250. That is the ratio. So I don't think I have much detail on the planetary gearbox and all those things here, but I might give you some reference, and there's a book chapter where we wrote something about that, and you can have a look at that. I can give you some. So I mean, I think I have given you materials already on the USB, but I might get some supplementary material for your like general, because I can't cover everything in this 12 hour, but I'll give you some supplementary material. We can pass it on to you by either you have the email, so we can email you, or if we give you a USB key, you can probably copy it. Yeah. So I can give you extracts from the 2 chapters I wrote. Because of copyright issue, I can't give you the whole chapter, but extracts on gearbox design for wind turbines, for example. And normally the way it's done, like for cars, the way you say the transmission ratio, it's actually the reverse in wind turbine. We say 1:100, say 100:1. Okay, so that's the convention. But essentially what you're doing is the gearbox actually is transmitting power from the low speed shaft to the high speed shaft. So if it's for 5 megawatt, 0.2 to 50 hertz, which is 1:250. And then gearbox design is a standard gear design for mechanical. And then obviously that shaft transmits power to the generator. The generator basically, in case of wind turbine, is an asynchronous generator. So I don't know if I know that various people with various background are here, but do you know about asynchronous machines or generators? Not really. Well, so normally to generate power, so have you heard of induction generators or induction machines? Okay, so basically it is the market share globally at the moment is mostly captured by a particular generator called doubly fed induction generator, and typically it's called DFIG, DFIG. So what it does, it's basically an induction generator, but it allows you certain variation in speed, so variable speed drive. That means you can cater for variation in wind speed. Wind speed is not constant, and an electrical generator is designed with an optimal characteristics, right? Your curve, generation curve is optimal. So if you want to vary that, then you can do that in the DFIG by either taking power out or injecting a little bit of power. And that is actually done in DFIG or doubly fed induction generator. That's why it's called doubly fed. However, I mean, the reason why induction generators are preferred because it's very rugged and used for industrial use. However, also fixed speed machines are becoming very popular, primarily for 2 reasons. One is the cost of permanent magnet is going down. So for all offshore applications, people are now using what is called permanent magnet synchronous generator, PMSG. Okay. And that's because the magnets are now more cheap. And this actually allows you to have more rugged operation, because in offshore, if there's some problem with the machine, you have to go and replace it. You know, if you're 50 kilometers off from the shore, and you have to go there, and nobody cares about there. Normally, normally inside the tower, they have elevators. So if you go there, you can go down to the foundation. And you also have elevators, so they can actually, this service elevators can take you up to the sun. So you can go up to here. but you cannot reach the blade. You know, for that normally helicopters are used actually. So helicopters go there and they have to do whatever is needed. So if you have to replace a blade, it's an enormous task, you know. Or if you have to look at the machine, do something with it, you have to reach this particular area and work there. So it's a O&M is a big thing in wind turbines. So so basically that's why that permanent machines are preferred, because they have more robust operations, and they are synchronous because they only work at synchronous speed, whereas fixed speed. But in this other case, asynchronous ones, they work at all of the speeds but the synchronous speed. Okay. So essentially, what happens is that you have a core and you have a field, and when the wind turbine is rotating, because of the interaction between the flux, essentially power is generated. So that is the idea in general. And how you design the core and how you design the magnet. So magnet is a permanent field, and the rotation basically causes the interaction between the two fields. So now you can have the rotor outside and the stator inside, or you can have it out reverse way as well. But these give you different kinds of design of generators. So as I was saying, like generator design has been done for the last 100 years. Say. But because of new applications and new requirements now here, people are again looking at generator design and making new generators. Okay. And I think somebody asked me yesterday, and we were talking about like optimizing wind turbines for urban regions and for application for small wind turbines. And that's one of the areas. There's a lot of work done on these kind of generators, but generators and optimizing generators for small wind turbines, not much research has been done because nobody is going to pay for it. You know, so that's why there's not much of interest there. So that's roughly the thing. So the main controls you can see are your yaw control here, the pitch control here, and then there are two other controls. I think we'll discuss those. Maybe I won't be able to complete everything by 1 o'clock. So what I'll do is I'll probably continue that in the next slot in the afternoon. But let me continue for another maybe 10 minutes or so. So we have discussed about all the things here. So these are really more or less things we'll also talk later, but this is to give an overview of what we're going to discuss and so on. Obviously, we'll look at number of blades, and maybe 2 or 3. And there's a reason for that actually, and I'll discuss again that in detail when we look at optimum number of blades and 1B momentum theory and so on. And that gives an idea why it should be. But typically for horizontal axis wind turbines, configuration with 3 blades is optimal. Rotor orientation, blade material and profile, the design of the hub, power control. We'll also talk about these in detail. One is the aerodynamic control, the other one is pitch control, which we'll also discuss today, but we'll also, or maybe tomorrow, what the details are in the slide. But there's also a detailed discussion on pitch control on day 5, actually. We'll talk about, as I said, some aspects of gearbox and drive and generator, and then I just mentioned to you about synchronous and induction generators and how they work and so on. So this is again a figure showing the inside of the nacelle, which we've been talking about actually last week, half an hour or so. So you can see that this is your, this is the hub casting is here, root joint winding here. You can see. This is the pitch adjustment mechanism. It's basically an actuator here. And then this is your transmission gearbox connected eventually to the electric system here. You have yaw motors here, hydraulic system. The hydraulic system is basically controlling the yaw motors here. It's an orifice damper actually. And then you have controllers here and electric system. This is again a schematic of what I've shown just now. And starting from here, you have the rotor torque here, given by N here, the speed of omega, the rotor shaft, then connected to the gearbox, and then the gearbox is connected to the generator. Generator eventually is connected to the grid. So here you can see, in fact, And on one side is the aerodynamics, on the other side is the power system. It's a unique situation. I mean, there's no other place where you have a coupling between aerodynamics and the power system. And then if you look at vertically, you have the geotechnics and then the aerodynamics. There's no other place where you have a geotechnics coupling with the aerodynamics. So it's all kind of, and through you have the structural dynamics, the composite materials, control systems, all those things. So it's a fairly complicated interdisciplinary interaction going on. And in fact, you can see that almost all areas of engineering are being used here. You know, aerospace, mechanical, civil, structural, control, machines, power system, economics, actually, you just name it. And even actually, when you're talking about wind turbines now, people are designing farms or wind farms, and they are communicating between each other. So you're talking about now wireless sensors and networks and communication as well. So it's a very broad area. And we have done some work on communication as well, actually. We have a paper in mobile computing on these protocols. How will you actually design the communication system? That's also a big area. We'll also discuss about aerodynamics and 2D and 3D aerodynamics. But essentially, most of the work people do in simplified analysis is based on 2D aerodynamics. The reason is the velocity in span. So if you take the wind turbine blade, you know, it has a span, very long, and then it has a cross section. The span-wise velocity is very small compared to the stream-wise. So that's why you can ignore the span-wise velocity. And if you do that, then you're only left with the cross section. So you only take the variation of the velocity along this. So the wind comes from this direction. So this is your wind coming in. This is basically your chord line. And this is called the angle of attack. So from your basic aerodynamics, those who have studied would know that this is called the angle of attack. And because of this, there's a force generated, which can be decomposed into two parts. One is actually in this direction, and one in this direction. So this direction is actually parallel to this. This is perpendicular. So the force which is generated parallel to this flow of the wind is called the drag. Perpendicular one is called the lift. You can also convert this into this normal and the tangential force. But these are responsible mainly for lifting the blade, and the drag is essentially causing a retardation. So our aim is to maximize lift and minimize drag, as is the case for an aircraft wing, for example. Also, because it's a two-dimensional system, so obviously, if you look at the force balance, if you have a force in the two direction, you also need a moment to finally do a force balance. So therefore, a pitching moment is normally created at a distance of c/4 from this tip of the blade cross section. And this is called the zero lift. The rotor plane is essentially, so the blade is like this actually. And we are taking a cross section of the blade. So the blade is actually rotating like this. So the rotor plane is actually perpendicular to the plane of this screen. So this is 2D, but this is actually what happens in 3D. And interestingly, you can see that in the wing, you have a complicated structure. This is actually the vortex that's generated in the wing. And this is a photograph taken from a ship propeller. You can see this vortex strips. So it flows like this. So this is a jet coming out. These are the vortex created. So similarly, you have these kind of vortex. So essentially, it's a 3D structure. So though for the blade, as I said, you can use a 2D airfoil structure and use the 2D aerodynamics, but essentially it's a 3D problem. And this will have very important and significant influence for wind turbines, particularly for wind farms. And this is a spectacular image from Horns Rev offshore wind farm, taken on 8th of February 2008. So there was a helicopter which was flying, I think, between the two islands of Denmark, and they took a photograph what was happening is that cold air at the rotor height and the warm air at the sea surface were being mixed. And that actually made this counter-rotating wave visible. But this has a very important implication. That is, this is an evidence of the turbulence of the wake turbulence created by the first row of the wind turbines. You can see, these are the first row of the wind turbine. So this created the wake of the turbulence, and obviously the other wind turbines were in that wake. The others also generated, but significantly generated by the first row, of course. The first row obviously didn't get affected because of this, because there's nothing in front of the first row. And these are visible because of this reason. So if it is not visible, it's there anyway. And the effect of this is that the turbulence was increased by roughly 30%, 40%. So that's a significant increase in turbulence. And the effect of that was, after a year of operations of this wind farm, all the blades of the wind turbines, except the first row of the turbines, had to be actually replaced because they were all damaged. So just think about this. I mean, this is a real wind farm, Day-1, and just after 1 year after commissioning, all the blades except for the first row had to be changed because of the impact the turbulence had damaged the blade. This actually shows how important it is to consider all these things. Apart from anything, it's obviously the picture taken is spectacular. And why this happens and why this air-sea interaction causes an amplification of turbulence is still not solved fully. And this is only back in 2008. So people had looked at this, and there are a lot of conferences just on amplification of turbulence and air-sea interaction in the last 5 to 7 years to look at this particular instrument. We'll be modeling the dynamic loads. Should I stop here, or do you want me to progress beyond this? I think it will take another 5 to 10 minutes. If any of the organizers are here. Okay, let me continue anyway. No, continue. So the loads mainly are gravity, the loads coming from the wind, which is varying with height, rotation of blades, and turbulence. We'll look at all these things in detail, obviously, but there's also additional loads like the waves, earthquakes, electrical, and grid faults. This is typically, if you look at the wind speed variation, and at a particular location, this red dot on the blade, and this is how the wind speed is varied. And there is, you can see there's a dip here. That is because when the blade rotates, when it is actually crossing the tower, there is a deficit of power or speed. That's reflected here. So at the time, so as soon as this passes this particular point, there's a dip here. And to see this in more detail, so this was a simulation done with a company called Siemens, actually, and one of my students was working with them. So we did a simulation of what is this called a tower shadow effect. So let's see what happens. So watch it carefully. The blade passes, and as the blade passes the tower, it gets deflected. You can see the blade is passing, and when it passes the tower, there's deflection taking place. Again, you see it's moving like this. So every time it crosses the tower, there's a sudden deflection of the blade. So this is basically the tower mass deflect. You can see again. Okay, just the wind speed variation obviously is another aspect to look at, and this is how it varies with height, and this is the profile of the wind speed. And normally it can be linearized,
like this. And then we can actually look at the wind speed also in terms of various laws, like power law or log law. And on the top of that mean wind speed, we also have a fluctuating component, which is actually the turbulence. And the atmospheric turbulence also is an important aspect of the scene. So we need to model all these things. And if you model the turbulence and look at the plane, then you can now see that actually this is something called a frozen rotor turbulence, meaning that you simulate the turbulence at a particular point in spatial field like this. So this is how it actually looks on a plane, and then you translate it onto the turbine. So the wind is coming, so you generate the turbulence in a particular location, then translate it onto the turbine. And the interesting thing to note here is that clearly we have these kind of vorticity structure. You see these circular structures. So obviously these are vortices, or vortex. And finally, we'll look into the offshore wind turbines and some analysis for those. But this is a floater with 3 turbines here. This is a single wind turbine on a floater here. For floating offshore wind turbines, you can have 3 different concepts. One is called a spot type. So this is a wind turbine sitting on the top of a cylinder like this. And these are mooring cables. This is a tension leg platform. So it's a platform. These 3 are actually taut cable. So there's a tension acting and keeping this actually in position. The third one is a barge type, which is more extended here, and then it has mooring cables. Now, out of the 3, this one is preferred because it has the least water plane area, because these are more extended, have more wave loading, and also this is more stable because you can see that this is more extended, so it has better stability. In fact, typically the spark type mooring turbines are mainly at a water depth of 50 meter to 60 meter. If you have to look at the wave loading, then we need to simulate the wave loading, and this is something we did with what is called a smooth particle hydrodynamics. So here we have looked at the waters, particles, and they're roughly 1 million particle wave taken. And you can see the wave coming in. So this is where your spar is here, or a monopile is here, the offshore formation. The wave comes in, hits, and then you have to simulate and see the pressure and the velocity like this. This is one particular aspect to show that various aspects, including hydrodynamics, is so important as well. And you can also have combined devices like a wind turbine and a wave energy device. So it's a platform here, it's a wind turbine, and wave energy devices are connected here. The 3 of those, like a bucket type wave energy device. The wave comes, it gets toppled, they're connected to a generator, and generates power. So this is actually being installed currently, and this is a project we are currently involved with this company called Floating Power Plant. This is some testing we have done on a liquid damper, which is usually located at the top of the wind turbine tower to suppress the vibration of the tower. So what happens when the tower moves due to wind or wave? The liquid here moves and sloshes and dissipates energy. And we simulate the wind turbine in the computer and test the full scale liquid damper in real time. And there's an actuator here you see. So the response of the turbine is fed here, and the response of the damper is fed back to the computer here. And there's a real-time communication that goes on with a fiber optic communication system. So partly computational, partly physical testing, but here we get the full design and the behavior of this liquid damper. So this is basically the computer system which does this testing with the scramnet controller here. This is the physical substructure, and the computer model of the numerical model of the wind turbine is actually done. Again, same thing. So sorry, I think took up slightly more time than expected, but we started a few minutes late, and I gave a few minutes break as well, so we compensated for it. So thank you very much, and I'll see you in the afternoon. But if you have any questions, feel free to ask them.
How does the blade get reflected?
Sorry.
How does the blade get reflected when it passes?
So what happens is that there is a deficit in the wind field because of the obstruction. The wind field is not uniform. So because of that, there is a change in pressure. Because the velocity changes, the pressure also gets changed, and that causes the blade to deform effectively. So this tower passage is more significant for what is called the downwind turbine. That means if the wind comes from behind, effectively, and in that case, obviously the tower obstructs the wind before it reaches the blade. It's more severe there, but it's also seen for upwind turbine if the wind is coming from the front side as well. So effectively, the tower is an obstruction. So around that obstruction, there is some deficit in the wind field, and that causes a pressure change. Effectively.
Are there any steps taken to contain the problem? Or is there any measures taken to contain the problem of tower shadowing, or still kind of insignificant over there?
No, yes. So I told you about the coning thing for the nacelle. Yeah, so what they do is they actually cone it in such a way so that the rotor plane is not vertical, it's actually an incline. So effectively, the gap between the tower and the blade is increased. That coning is done essentially to account for the tower capacity effect.
So does it have any effect on the low cycle fretting on the blades? Because it's
because if it's operating and every blade encounters the tower once each during the, so if your speed of rotation is omega, then that is basically omega times the number of years. You can multiply and see how many times it's doing. And yes, of course, yeah. It's not insignificant, that's the point here. It does deflect a lot, actually, as you could see there. But that's why they have to do it, they have to change the angle so that it doesn't hit the tower. And that's a more critical problem for offshore wind turbines, because for onshore, the foundation is fixed. But now if you have wave load coming and the platform is moving, then you don't have the control of the platform as well. So people are trying to also control the motion of the platform.
So this problem is significant only for the large, very large scale wind turbines.
Yeah. Well, I'm sure it's there for other as well. How is the pressure deficit happening and how it's changing depending on flow parameters.
The pressure deficit is only because of the obstructing tower.
Because if the tower had not been there, there had been a free, upstream would have been free, downstream would have been free. So then there's no effect.
So if there is any particular region along the tower, can that be remodified with the lattice structure and see the effect on the blade coning?
Yeah, but the point is that there's also, like, if you have to do that, then the tower design will have to be modified. Now, tower design has been done based on a lot of other constraints and conditions. So if you change the tower design, then you have to look into other things as well. It's not that you can't do it, but you have to look at what net effect it might have. But it'd be easier then to just take into account the tower deficit effect and tower shadow. But in fact, there is a code called IEC 6400, which also gives you how to account for the tower shadow effect. So what they suggest that you take a certain amount of load for tower shadow as well, add it to your load. Basically, you have to do various load combinations for the design of the turbine. So that would be one load combination.
So in case of large turbines, will this 2D analysis be sufficient because we have variation in the longitudinal direction as well?
Yeah, so for large wind turbines, even 2D analysis with what is called, we'll see later, blade element momentum theory is used. with certain modifications for tip loss and some corrections. However, saying that when the wind turbine blades goes in stall, deep stall mode, you'll see the behavior is very different. And in that case, obviously, a more detailed CFD analysis might be required. And I think they do it in some cases, but for preliminary design, blade element momentum theory is sufficient. But then again, a lot of things which we do not take into account, like there are unsteady aerodynamic effects. They are not fully accounted for in design. So even I've spoken to people who are in, say, Siemens or Vestas, they don't even, they assume a lot of things. There's a section called load section. There's basically this load section. They design the blades or all these things with certain assumptions, and they assume aerodynamic damping of some kind. But they don't even know whether that's correct or not. So that's why they sometimes measure, they try to see if their model is correct. But again, this area is not very mature because people are designing these kind of wind turbines only for the last 10, maybe 15 years. So even the expertise in this area is not that high. So the wind turbines, like big wind turbines, haven't been around for more than 5, 6, 7 years. People have also looked at other things like the trailing edge and flaps and so on, but then they don't like to put anything outside the blade because that has other implications. So,
is there any limitation for the length of the wind turbine blade? Well, because as we go longer, there will be the effect of buckling can take place.
Yes. So yes, well, not in terms of total length, in terms of, so the wind turbine blades are not manufactured as a single shot element. So what they do is they make parts of those, and those are then transported. So there is actually a constraint on how long can you transport actually. Your drop length actually is a constraint there. And they do a buckling analysis on that actually to see whether the panel will buckle or not in fact, while transportation. So that becomes maybe that becomes more critical than the overall buckling. But in terms of the length of the blade, basically it comes from the amount of power that you can generate. And the power generation is guided by your generator actually, electrical generator. So the generator that you design will decide how much power you generate. And that power basically will decide what the blade size will be. And the generator basically sizing will be decided based on what is called micro-siting. That means for a particular site, what kind of wind resource you have actually. There's no point in having a generator of 2 megawatt if you can't generate 2 megawatt most of the time at a particular site. And that happens actually for a lot of these cases. As I said, expertise is very limited. So people have designed, but wrongly designed things, and those are non-operational. Like wind turbines are there, they're not operating all of the year. But it worked for them because, say, for example, wherever they did it, and that's why I was saying about this policy is very important. So government pays for the amount of electricity based on your installation, not on generation. So if you install the wind turbine, you get something, irrespective of how much you generate. So
I think as a precursor, we must get the historical data of the wind.
Yeah.
That is as a precursor.
Yes. So I have an assignment actually, either today or tomorrow, I can't remember, on microsighting. So I'll give you some data, an assignment. I'll give you a link to a website from where you will download some data and do a microsighting to analyze a particular site to see how to choose a wind turbine design, generator, and spec for a particular site. So say you're a consultant or you work in a company and some client comes to you and says, oh, I want to put a wind turbine. So what are the procedures you should do actually? So as you said, like as Professor Day said, that you have to first look at the site to see what the resource available is, so which is called the microsighting. That you have to do. And that will tell you what is right for that particular location. So if you have some data here, maybe you should do it go on campus and see. I'm sure there is some meteorological data available from somewhere. Well, I'll give you a link, but feel free to use other data. I'd love to see how it compares to other locations.
Is there about the clean energy and also related to the global warming, rising temperature and sea-water rising? But when such a big wind turbine is rotating, there could be turbulence, and I think the entropy of the air increases, like it's moving and it's still contributing to the global warming or the rise of the temperature. And when you compare this with other energies, they give more power than of wind turbine, taking the condition down.
So this is where the whole thing about sustainability and life cycle assessment comes in. And the way you do it, you can get different answers. Actually, I can give you various problems where you have various answers for various things. For a particular wind turbine, for a single wind turbine, essentially the impact would be negligible compared to the amount of other greenhouse gas emissions, the carbon that you emit from other sources and generating powers, and so on. So therefore, I don't think there's a fair comparison to say that, because the amount of clean energy you generate will offset all those negative things. But for a wind farm, people have done studies to see if you actually have, say, a significant area of sea with wind turbines, then what impact it would have on, say, for example, the formation of clouds and how they move and so on. It might get affected. But as of now, I think the other problems are so pressing that this will be actually very small compared to the impact.
So I was wondering, we're only talking about the turbines that is surrounding in a horizontal axis. Is there any turbines that, the blades, which is rotating in the vertical axis? Because it would be more symmetric than of, the setting you said and the.
So we'll see that power is proportional to cube of the velocity. So if you have a vertical axis wind turbine, the wind speed you get actually is like, say, roughly from the ground level to a certain point. And then you get some sort of an average of that. But in case of horizontal axis wind turbine, all your blades are located at the top of the turbine. So now if you compare the wind velocity, I've shown you the profile, and cube that, so your overall efficiency for vertical axis wind turbine will be much lower compared to the horizontal axis. The only case where it will work is if you do not want noise, then for urban setting, smaller horizontal axis, vertical axis wind turbines have been used. But also with the caveat that what happens is that the lift force required to rotate that is significantly high. So you cannot cut in. Once you cut in, then you may actually generate power, but the problem is in cutting in. So yeah, we have also done some research, and one of the problem is that. But for urban setting, yes, vertical axis has been used mainly because of the noise issue. Because if you put a horizontal axis one, then the speed will be very high actually. That will generate a lot of noise. So if you don't want to generate noise, then
also it will be coupled with this function, right?
Yeah, but we're talking about a small one. And here we're talking about huge turbines. You can't have vertical axis for this kind of turbines and expect to get the same kind of power. Simply, skew global. Yeah, I think.
So with this, that's the end of this session. So next session will be starting. Will be started at 3:30. So please join us at 3:30 today.